bond is unambiguously determined, so that's kind of that's a really nice thing. Like, some of these reactions you'll get, you know, this reaction results in a mixture of products. When you get to like actually in the lab, that is so annoying, because are you gonna get, honestly, nobody ever gets 100% yield anyway. So at best, you're still not gonna get 50% yield and 50% yield. One of those might be favored. Is it the one you want? Maybe.
I got 110% last week.
Fair enough. So yeah,
I'm doing great.
Fair. The only time in organic lab that there is 100% yield is when there's still solvent weight or impurity weight in there. Because organic chemistry doesn't behave. Yeah.
So if there were like two ketones or two aldehydes, it kind of function the same way as the previous example we looked at, where the aldehydes would probably be favored over the ketones.
Ask me that again once we go through the mechanism, and I have the mechanism on the board to look at, and I've talked through it. That will be a more educated guess. So, yeah, you stick a phosphonium on a carbon, and then you get really aggressive to deprotonate the carbon, and you get a phosphonium ylide. Yeah, phosphonium ylide. If I ever get a little too, like, I do this a lot, just nouns are sometimes harder, there's just so many things, I would rather just point and say that than like accidentally say nucleophile when I mean electrophile or vice versa. So if I ever start doing that too much and I stop using nouns, again, that's a situation where you can and should stop me and force me to use nouns so that you understand what's going on. So, yes? Okay. Please interrupt me with questions. For real. Okay. Let's try, oh, sweet, okay. I'm gonna push over here more before it's visible. So, let's start this guy. We are going to do, and this is a Wittig reaction. Yes, it starts with a W, but chemistry is mostly French and German, so. We got that, and we got okay. So, where's our nucleophile? It's conveniently labeled with a negative charge, right? Love when that happens. Electrophile. Well, our electrophile is where it's going to be for all sorts of chapters for a while. And so we begin. We attack there. Can't just leave it like that, right? Because that's leaving points, easy points on the table. Even if this is the only step that we know, this is still leaving easy points on the table, right? Because I just drew a fifth bond to that carbon, so I have to bump that up, yeah? Now we stopped leaving easy points on the table. All right. We do that, and we get, okay.
I don't like the R2, we're just gonna actually draw that.
It's fine. this is our new bond. This was originally that carbon. That's not a G. That's still a CH2. And that. And yes, I'm drawing in a square for a reason. We're gonna do some wild stuff with this. Okay, so, far enough forward to not. Okay. So we start with this. We make a new bond, and this guy is a dipolar intermediate. So intermediate is just, like, that's just the word we use for whatever we can draw, basically, to get to our reaction, but like, this isn't the final thing. And honestly, usually it's not always not able to be isolated, but usually you can't isolate these, or you can't get them easily isolated, intermediate. And this guy is called a beta-ene. No, I'm not gonna make you guys memorize the names of like beta-ene and what's the phosphonium ylide, and like if I use the word phosphonium ylide in a test question or a quiz, in a test question, I'm definitely also going to be saying like Wittig, or I'm going to be drawing like the thing, right? Okay, cool. Because I hate memorization, and I want everything to be as much like, from the rules that I know, I can try and problem solve. That's what I personally prefer to do, so I try to make it that possible. So, this guy collapses into a four-membered ring, and we get I'm not redrawing this. And we get a nice four-membered ring. Are these sterically preferred? No, I mean, not really, but like, chemistry is, because we always talk about what happens with tiny things, and then we're always taking, you know, even if we do small, like micro-scale organic chemistry, there's like billions or more of these in there, right? So we're just taking tons of these and just mashing them all together. Chemistry is basically a like a statistics game, sort of. Like, even if things aren't favored, if it's able to happen, and if when it happens, it progresses in a reaction that like will take it further down the road in this reaction, so it won't contribute to the equilibrium of this thing happening and then undoing itself, then you will probably see that happen to some extent, which is why in really nice straightforward reactions that are like, literally nothing else should happen, you throw everything in and you're like, yeah, I have to heat it, but it's fine, and you heat it and you stir it, and then the whole thing is brown. Or if you scorched it, black. Is your product still in there? Yes. Is it probably white, off-white, or yellow? Yeah, probably, unless you're a metally person, or unless you get real aggressive with the double bonds, like really super, because it is hard to get out of the yellow range. Also, four-membered carbon rings are possible, right? Like, you can get them. They don't break if you blink at them wrong. And phosphorus and oxygen. Oxygen's bigger than carbon by, yeah, bigger than carbon by a little. And phosphorus is like a whole valence shell bigger than carbon. So that's also helping stabilize this. So, oh, and this has a name. Oxa. Yeah, no, hell no. I'm just writing these because I don't know, because I feel like you're missing out on stuff if I don't put it up here, but I'm refusing to show you like the mechanism that they have up there because it's just not the same to like point at a done mechanism and not see it drawn in front of you. I don't know. It just, I never learn anything from like watching someone talk through a mechanism that's already drawn out. Okay, so actually let's grab this. Because the next step, okay. Okay, this, basically, it collapsed to a four-membered ring, and then this guy goes, all right, I'm sort of gonna, they don't call it collapsing, but it breaks a bond. I'm gonna call it collapsing, because, I don't know, this whole thing is breaking. This
Say
goes
collapses.
here.
They say collapses.
Okay, I know they say from here to here they say collapses. I don't know if they
Oh,
say
you're right.
from here to the next one it collapses, but this feels more like a collapse than this. Although I guess, to be fair, this doesn't have to be drawn so close to a square, so this is like all spread out, and then it collapses into all compact. So all right, fine. What they say works. It just doesn't look like it because I drew it this way. But now we get this. And notice I drew my arrow pushing, electron pushing arrows. I drew the mechanism arrows from the bond to the bond, not to a specific atom, which means, stop rolling, that we get, so this whole coming from here means that bond's breaking, coming from here means that bond's breaking, going to here, we're getting a double bond, going to here, we're getting a double bond. So we get PH3, I don't want to draw it at a right angle because that's ugly, but I don't want to like, I want to keep this. So PH3PO, I just want to keep everything where it is because they haven't completely changed and I don't, why spatially rearrange all of this when you don't have to? Then let's see, we have an alkene. This guy. This is triphenylphosphine TPP. So this is triphenylphosphine oxide. Yeah. So this is a mechanism that is going to, like, yes, know this mechanism, and it's a little bit harder and requires a little more along the lines of memorization than most of our, or than what we've seen before. Because what we've seen up to now is just find a nucleophile, find an electrophile, do an attack, check the charges and the acid base, and do you need to go back and do a step before the attack, or are you good now? Okay, do the workup, get rid of your stuff, do the stuff at the end, and then there you go. Yeah? The stuff in the stuff is just water and acid workup so that you don't have O minus. You've got like OH groups or something. But so this is a little more along the lines of memorization, but yeah, also know this.
So those two are separate things, right? Like two different molecules?
What are, oh, these guys, yes, sorry. That overlaps and makes them look similar. But yeah, no, we broke, red. We broke that bond and that bond. So now we've got, and I mean, they draw it PH3PO and I guess that. It rearranges, that still looks like it's running into each other. I'm trying to make those not visually run into each other. So that is more normally oriented. I just wanted things physically where they were.
Is TPP useful?
Triphenylphosphine is, I mean, yeah, it's pretty useful. I wouldn't say it's a really good, I don't want to say it's exactly a really good leaving group because I'm not sure if that's, I'm sure that has some sort of implication that I haven't fully thought through. So I don't know if it's a really leaving group. I feel like it doesn't take electrons with it, I don't know. But it is a, 3 phenols on the phosphorus have a bunch of electron withdrawing things, and this TPP, triphenylphosphine, is a really common ligand, or at least a really common component of ligands when you end up doing carbon-carbon coupling, which is mostly palladium. Yeah, most of those are palladium. That's what won the, don't tip. That's what won the, I don't remember what year, but the Chemistry Nobel Prize semi-recently, and by semi-recently, I mean I was in secondary education, wait, this isn't secondary, post-secondary. I was in some level of post-secondary education by the time the Nobel Prize for Chemistry was awarded to palladium catalyzed carbon-carbon coupling. But also I've been in post-secondary education since 2011, so that's what I mean by semi-recently. God, I TA'd my first year here, and then I worked for the library and didn't teach, and all of a sudden I got back in the classroom last year, and I kept making references to things and going, oh God, no, we didn't, oh, you guys are not as old as I am. Oh, how old am I? And now I already know it, but I keep surprising myself with it anyway. Here's the deal with this guy. I think that's a really cool mechanism. I think it's not a bad idea to know it. But remember, there is no situation on an exam where I can give you just one mechanism and you definitely have to do that one, right? So there's always an out. There will always be an out from doing this mechanism unless it's on a quiz, which it is timed, 30 minutes, and you should shoot me an email on or before Monday if you have any sort of time, additional time or whatever accommodations, just because I don't want it to be a problem on Tuesday, because I gave him a pep talk and was like, since it's open note, be somewhat strict on the timing. So I told him that, so I don't know how strict that's gonna translate to, but yeah, so if you've got extra time, you don't have to deal with the other place where you take things. You can if you want, but you can just come hang out at my office and take it afterwards. But if you have to do this mechanism on there, it's open internet, so, you don't have to memorize this. You should, however, be able to see these two and figure out what products it makes. Yes?
I answered my own question.
Okay. So if from this you can at least do this nucleophilic attack, then if you remember you're making a new carbon-carbon double bond, you're replacing this double bond with a carbon-carbon double bond. That should be enough to get you to, here I know what the products are from this, even if I don't know the mechanism. Yeah? Cool. But man, I like that mechanism, so who knows? Maybe you'll get credit or extra credit on the exam for being able to do it. Okay, yeah, so examples. If we start with this guy, and this is another situation where because we're writing out this P and we don't write out carbons, it's really easy to accidentally add a carbon because when you break this bond and then you go to draw this shape again, you really want to draw that last line and then end it at nothing because you got rid of the P. And that's adding an extra carbon. So that's why I always think it's a pretty good idea to, before you redraw it, mark or circle or color in or whatever the nucleophilic carbon. Because trust me, it helps. It helps me not mess up in front of you guys more often. I don't just do it for your sake. So basically we take that carbon and replace that oxygen with it, and now they're stuck together right there. Bam. Did this say something about retaining stereochemistry? Oh, wait. Did this say something about being?
I think it's on the next
Yeah.
slide.
Oh,
Yeah, it's the next.
There we go.
sweet. Glad you guys have, yeah, okay, cool. So, same thing, find your nucleophile, replace the oxygen with that, draw your stuff. Oh, here we go. If I had looked directly below that, I would have seen this one, where we get a cis and a trans. So, there we go. I guess we get both. Oh, and this one is Z selective. So we get a little bit of trans for E, and we get a whole lot of cis or Z in this case. Okay, yeah, next question, we'll talk about that. Let's see. This one, only the E isomers further, and that's that. Is that different from this guy? Okay. Okay, yeah. Some are Z selective while others are E selective. Basically, if you've got an anion stabilizing group, so carbonyl groups, they really like to take those charges and be like, hey, don't worry, carbon. I know you're really uncomfortable with having a charge, because if you have a charge, that means you don't have 4 bonds. You love to have 4 bonds. It just makes you uncomfortable. It's fine. Don't worry. I can deal with that. I'll have the charge. And even still, everybody gets to have a full octet. Perfect. So if you can do resonance like that, this guy is much more stable. Usually more stable equals less reactive, right? So really stable, or really unstable, like organolithium or Grignard, aggressive, really reactive, and oops, it's easy to kill them because they'll react with all sorts of stuff, not just what you want them to. This guy is even more stable, so it'll stick around longer. So yeah, if you've got that, you're E selective. Is E always trans?
Yes,
Okay, E is always trans?
I think so.
Okay, and Z is always cis. Thank you. If that's not the case, somebody do a discussion board post or something to correct me, and link your source or whatever.
I mean, like the potential.
I believe you, I'm just,
Cyclo, like rings. I don't know if you have bonds with rings, if that.
I don't know.
But like,
We're gonna go with E is trans.
yeah, it's when the
Yeah.
priority groups are
The
on
priority
opposite
groups are this way.
sides.
Okay, yeah. So E is trans, just more inclusive of if you've got 3 things instead of just 2, and Z is cis. And I'm just gonna keep using cis and trans because like those mean something to me. Like cis is same and trans is
Oh,
opposite.
I
Like,
say against and together.
against and together. That's good. All right, I'm down. Yes.
You could say like Z same side.
Z same side. Ooh, I like that too. Okay, against and Z same side. So, we're gonna use those as interchangeable. And when I say trans or cis, I might say that even if there are 3 or 4 substituents, and I mean E or Z, or I might do interchangeable that way, even though E and Z are always the correct answer, and cis and trans are only appropriate if there are only 2, like 1 on each side. It's fine. And since I'm going to use it that way, you guys are allowed to do that too. So you get trans if you have resonance stabilization or some sort of anion stabilizing going on here. You get cis or Z selective, Z same side if you can't stabilize that. Yeah? Can I tell you why? Nope. I wonder if I knew why last year. I kind of want to know why. I'll look that up, and if it's relatively easy enough to explain, if it's something I can confidently explain and it's interesting, I'll post it later. But it's not on the slide, so you don't have to know it. Okay. What, 15 minutes left? Yeah. Okay. We're on like 15 and 54. That's fine-ish. Okay. The Horner-Emmons-Wadsworth modification of the Wittig reaction. No, I have no idea if I'm saying any of those correctly. Probably not, if I had to guess. These guys use a phosphonoester derived from an alpha haloester or derived from an alpha haloester or a ketone to generate the Wittig carbanion. So basically, you do, let me see if I've got, no, okay. Okay, yeah, so this is just a modification on the Wittig reaction, which means this is pretty much how it happens. It's just that this is the way that we make this guy. And this guy acts as our carbon nucleophile. We use alpha phosphonoesters ketones. They're formed by 2 successive SN2 reactions. SN2 is backside attack, or SN1 is? SN2 is, right?
Yes.
Yes? No? Yes?
Well, SN1 creates mixed. SN2
Yeah,
is always
SN1 creates
backside.
mixed, so the leaving group leaves, and then you can attack from either side.
Yeah.
SN2 is backside attack because you always invert the stereochemistry. You attack, and then it leaves. It's not a good enough leaving reagent to just piece out on its own. When I ask questions like that was a 50-50 guess. Like, don't do I'll just say yes because that sounds right, and I want to, and she's probably, there's more than a 50% chance that she's right, and then it sounds right to me. That was a flip of the coin guess for those. Okay, so yeah, you do 2 SN2, so backside attack. You attack there, and you kick off bromine, and then over here you have the bromine goes, hey, wait, no, me, and you could go to this, and you get that nice little, that attacks that goes over there, you get rid of this dude, and that becomes a double bond with 2 of these guys. Those guys stay there. I wish that they had just put the double bond O this way and kept the 2 others this way, because sure, this is right, and yes, traditionally we try to draw carbonyls facing upward if we can. But like, make it visually similar so that it's obvious to tell what's similar? I don't know. If I wrote a textbook, maybe someday I will. So, we get this guy, treatment of a phosphonoester. We're gonna take this guy and use a strong base because, you know, it's not exactly a negatively charged carbon yet. So we're gonna use a strong base to make this a better, basically we're gonna use a strong base and we're gonna be able to deprotonate this. This is not going to show up on your pKa chart, but what will show up on your pKa chart is, at least this, the carbon alpha 2, so carbonyl alpha, beta, gamma, etc. We'll go over that later. The carbon right next to, or alpha to an ester is pretty acidic. Like, and when I say pretty acidic, not like carboxylic acid level acidic, but like pretty acidic when you're comparing to, well, the alternative is pKa of like 50 something because it's a carbon-hydrogen bond, right? So, just from that, in your pKa chart, you can see this pretty acidic. You put another thing next to it that's all electron withdrawing and, you know. So, add a strong base to make this guy a really nice nucleophile, and you do the same thing. You replace this oxygen with the carbon in question, and you get rid of this half of the stuff, and you leave the ester part of it. And you get the E isomer because, well, we always have this anion stabilizing group, so we always get resonance stabilization, so always E.